All right, now that we're starting to get into some proofs, we're going to introduce some tools that are going to be very useful to be used when writing those proofs. So it might be a wise decision to write these down and keep them on hand because you'll be using them in your assignment, and it's going to be good to know them as we move forward. So the first one of these is called the reflexive property. Reflexive property. And the reflexive property is basically saying that something is equal to itself, or something is congruent to itself. Very profound, I know. So let's say we had a segment AB here. We could say that AB is congruent to AB, and our reason would be by the reflexive property. We could also say that the distance AB is equal to the distance AB, and that would also be reflexive. So if anything is equal to or congruent to itself, it's the reflexive property. Okay, next we have the symmetric property. Now, if something is symmetric, you might recognize this keyword here, symmetry. It basically is saying it's the same on both sides. Well, that's the same thing here. Let's say we had a segment AB and we had another segment CD, and let's say that we knew that these were congruent. We could say that AB is congruent to CD. Let's say that's our given information. That's given to us. So then next we could say that, all right, well, if AB is congruent to CD, we can also say that CD is congruent to AB, and that's by the symmetric property. So if we switch those two around, so first we had AB was congruent to CD, we switched them, we said CD is congruent to AB, which is going to be true, right? Because if it's congruent one way, it has to be congruent the other way, and that's by the symmetric property. Next we have the transitive property. Transitive is kind of like symmetric, but it's taking it one step further. Let's say we had some more segments here. Let's say we had AB, CD, let's say we had EF over here. And let's say we were given that AB was congruent to CD. So let's say, all right, we're given AB is congruent to CD, and we're also given that CD is congruent to EF. So we also know that CD, and we already have one mark here, CD is congruent to EF. So the transitive property is saying that if AB is congruent to CD and CD is congruent to EF, then we can say that AB is congruent to EF. It's kind of transferring through the CD and connecting the two on each end. So if we wanted to, we can say that AB is congruent to EF, and our reason would be the transitive property. All right, let's say we were given that AB was congruent to CD, and whenever we use the definition of something to make another statement, that's our reason. We say it's the definition of, and whatever word gave us that that information that lets us say that. So here, if we wanted to say AB is congruent to CD, we can also say the distance AB is equal to the distance CD. Remember, this is talking about the segments have the same measure. AB and CD, those are the actual distance between those. So these are two different statements. But since we knew that this was congruent, we could say this statement, and our reason would be definition of congruent segments. Definition of congruent segments, because we know what congruent means and it lets us make this statement. And we could even go back right where we started from, because we know AB equals CD. We could say that AB is congruent to CD, and if we went this direction, this would also be definition of congruent segments. Whenever you use a word meaning to make a statement, like here we used congruent, you always say it's the definition of that word. So here we said definition of congruent segments. Alright, this is an important one that's going to be very useful, and we've actually already worked with this quite a bit in our last chapter. This is just segment addition. Remember, we could add these small pieces together. We could say that RS plus ST, and those two small pieces always add up to equal the big piece, right? So if we had some situation like this, and we could say, and we wanted to say that RT is equal to, the big piece is equal to the two small pieces, RS plus ST, added together, right? The big piece RT equals the little piece RS plus the little piece ST. And whenever we make that kind of statement, we just say segment addition, because that's all we're doing, is we're just adding the segments together to give us the big piece. Alright, the last one we have here is called substitution. And substitution is just like you might think in sports. When the coach wants a sub, he takes one player out and puts another one in. He substitutes another one in for him. So whenever you take some value and you replace it with a different but equal value, that's called substitution. So here we have some segments over here. We know we're given that AB equals XY plus YZ. They told us that. And then we know that also XZ equals XY plus YZ, which makes sense. That's segment addition. XZ equals XY plus YZ. Now notice that these two values here, XY plus YZ and XY plus YZ, are the same. So what we can do here is, since we know that XY plus YZ equals XZ, we can substitute in XZ for this value. So we can take this XZ and we could replace it with, we could substitute it in for XY plus YZ, because we know they're the same. So if we wanted to make a statement, we could say that AB is equal to XZ, and that's us replacing XZ with XY plus YZ, and our reason would be substitution. So whenever you take something out and put something else in for it, that's substitution.